All right, good morning, ladies and gentlemen. We're still chilling out here in section 7.3, but now we're in section 7.3b, and this is going to be called the washer method. And what the heck, the washer method, not the kind you wash your clothes with. We're going to be making washers where here is going to be my area that's rotated, okay? And we're going to create a hole in the center of our washer. Well, how are we going to do that? Very carefully, all right? Well, tell you what, how we're going to do that? We're going to do that the same exact way we've been doing the other ones, all right? So what we are going to be able to do is we are going to revolve or rotate an area region by f of x and g of x around the x or y axis. We will do one of each of them today, and then we're going to find the volume of the solid created by this action, okay? Well, if we rotate about the x-axis, well, it's going to be the same old deal as we did before. What are we going to do? We are going to graph our function. So let's say, I'm just coming up with a generic function. Let's say this is my f of x function, and this one is my g of x function, and what I'm going to be revolving in this case is this area right here. And as I revolve that area, okay, if I revolve that about the x-axis, like that, well, what happens? Obviously, well, maybe it's not as obvious as I think it is, but we will create a solid with a hole in it. So if I drew my rectangles perpendicular to my axis of rotation, but I'm only drawing my rectangle inside my shaded area, and then what I'm going to do is I'm going to attempt to draw my reflection, and this is going to kind of come down like so, and this top one is going to kind of come up like this, and I don't like that first one, so let's go back, let's take this like that, and then this is going to be, still missed it, but that's okay. All right, so let's go back. I told you I'm not good at these, so I'm going to come up, and I'm going to come down, and I'm going to make sure I'm hitting about here. So there's that one, and this one's going to be coming up. I can't even hit the stinking spot. So there. And what I'm going to do is, when I revolve this, I'm revolving this rectangle all the way around there, right? And granted, it's not too symmetrical. However, what I'm going to do is I am going to draw, I'm not drawing the whole thing this time. I'm going to draw half of my washer. Oh, what do you mean, half of my washer? Half of my washer. There's my washer. It almost looks like a sliced piece of cantaloupe. It's half of a washer. I will only draw half of washer. And if you ask me why, I'm going to say because it's easier. It's easier to draw. That's the only reason why I'm only going to draw half of it. It's hard to make that whole thing in there and still look good, but we can kind of see that half of the washer is right in there. Okay? There it is. It's half. Well, so what we need to find out is well, how do I find the volume of a single washer? And the volume of that single washer is basically going to be, well, if we went to the washer factory, how do they make a washer? Well, they take the volume of the outer disk minus the volume of the inner disk. Okay, So bottom line, what we have is we have an outer disc, and we just have a flat sheet. Then we stamp a hole out in the middle, and we make a washer where this is open here, and this is going to be the solid generated when I rotate it. Like if I rotated a sphere, I would make a donut. I don't know, donut with a hole in the middle. But that's how I'm going to find the volume of a washer. Well, if I take this a step further, well, a washer is still a circular measure, or still a circular object. So really what I'm doing is I'm finding the volume of my outer disk minus the volume of my inner disk. So the volume of my solid is going to equal my pi from, where am I going? I guess I better come back and say where I'm going from. Where I'm going from is I'm going to be going from, well, notice this is going to be perpendicular to my x-axis, so I'm going to be going from A to this intersection point, which is going to be B. So if I did that, I'm going to be integrating from A to B of my washer. Well, what is my washer going to be? Well, when I'm looking at here, I'm thinking of an outer disk. Well, this is my radius of my outer disk there, isn't it? That's going to be from there to my outer disk. And I'm going to call that outer disk R squared is going to be my height times dx, because it's perpendicular, minus my pi integral from A to B. And now I got a smaller one, because now here's the radius of that inside. I'm going to do that in a different color. Why? Because I don't like that one. And I'm going to make it black. So I'm going to go, there is my inner one. And I'm going to call that inner radius little r, because it's smaller than the other one. And then I'm going to square that with a dx. So I'm really, to find the volume if there's a hole in it, really what I am doing is I'm taking, this is my outer radius, and this is my inner radius, okay? Because I can see that on the top, if I really am coming back through here, my outer radius, my big R, this one, well, that is really, that's my big R. And my inner radius that I did in black, well, that's really this guy, and we're going to call that little one. So in order to find this, okay, I'm going to subtract those two radii to find that. However, please understand, we are taking the volume of the outer disk minus the volume of the inner disk. And when we lay it all out like this, oh, you mean we have to do two integrals for all this? No, we don't, because we have those things called properties of integrals. And our properties of integrals are going to allow us to say pi integral from A to B. Both of these integrals are going from A to B. They are both in terms of x. So I can take my big radius squared minus my little radius squared dx, and I can compress them into one integral. And this integral right here, this is my washer method. Okay, my washer method is taking big radius squared minus little radius squared. Now, I want to take a step further here, and I'm going to try to get this a little bit closer. And nope, I didn't want all that stuff. So I'm just going to take this up here. I want to get a little bit closer to my picture and understand that. Okay, that's my washer method, number one. And I'm just going to delete that for a second. And as I'm going through here, it's really important for you to understand that this washer method right here, it's actually the difference of two disks. Okay, it's actually found by the volume of the outer disk minus the volume of the inner disk, just like it's posed over here. Okay. Also, very important to see that this value right here, or this expression right here, is not the height of the rectangle. It's not the height of the rectangle. It's two separate integrals. If I needed the height of the rectangle, I would be taking big R minus little r. This is the height of the rectangle. And I can't take that and square that and find it because I need to take the volume of the outer disk minus the volume of the inner disk to get the area of this washer, all right? Well, how are we going to do this? We are going to go through this. We're going to do a couple examples, and I'm going to turn her off. So what we're going to do is we are going to revolve the area bounded by y equals x squared plus 3, y equals 4 about the x-axis, and we're going to find the volume of the solid. Well, big deal. So I got 1, 2, 3, and this is a parabola opening up like this. I don't like that last one because it's not very symmetrical. And then I'm going to take y equals 4. Y equals 4. This one's y. Come on. Oof. This one's y equals x squared plus 3. And I'm taking this area. I'm going to make that a little bit bigger. It'll be okay. I'm going to make this one here a little bit bigger. And this is going to revolve about the x-axis. And if I'm revolving the x-axis, I'm thinking dx. Okay? And when I revolve that about the x-axis, what? I'm going to draw a reflection. Well, 1, 2, 3, 4. Well, if I'm drawing a reflection, I'm going to say 1, 2, 3, 4. And I know I'm going to have this coming across here. And I know I'm going to have this coming across here. And if I drew my rectangle anywhere I want in my area region, I'm going to see that same rectangle down here. Okay? And that revolved it. Well, that's my reflection. Now when I revolve it, now I need to see my rectangle in which I have revolved. Right? So there is my solid. So I can see inside here, there is a large hole in the middle. And here is going to be my rotated solid. It's going to have a big hole in the middle of it. It's a cylinder, kind of, oh, I don't even know. I could draw it, but it's going to be a little funky. But I don't need to draw it because every time I set one of these up now, if there is a hole in it, it's a washer. When I revolve this, there's going to be a big hole through it. Therefore, it's a washer method. And whenever I think of a washer method, I'm thinking of the integral pi times the integral from a to b of my big radius squared minus my little radius squared. And in this case, I automatically know it's going to be dx because that is where my thickness, if I extended that rectangle down to the x-axis, my thickness will be measured on the x-axis. So that is, excuse me, where we are going to be at. Well, as I'm coming through here, I have a big R. My big R is my big radius, big R. Well, I'm going to find that big radius from my center of rotation out to that curve. Well, that curve, remember, because the height of that, this is going to be an xy, that's a y value. Therefore, the radius is going to be 4 for my big R, and my little r is going to be from, what color do I want? I'll go on black again. From my center of rotation to my inner radius is going to be my little r. And notice that's also going to be a y value, and that is coming to my parabola. So there is my little r. Little r is going to be x squared plus 3. And technically, it's curve minus curve, so technically there's a minus 0 and a minus 0 on both of those, because it's upper minus lower to get that radius. But I don't need to because I'm on the axis, so I'm just ignoring those zeros. Then I'm going to take my big R and my little r, and I'm going to say, I don't like that color, that's what I'm going to say. And I'm going to take this volume, and I'm going to say it's pi from where to where, and I do know it's a dx. Well, what's my big R? Big R is 4, so I need to take big R of 4, and I need to square it, minus, what's my little r going to be? Little r is x squared plus 3, x squared plus 3, and I need to square my little r. Now, my limits of integration need to be in terms of x. Well, where am I going from? My discs or my washers are going to start from that point to that point. Well, what is that? Well, that is when these two equal each other. Well, when does x squared plus 3 actually equal 4? Well, that's when x squared equals 1, so x must equal plus or minus 1. So these are negative 1 comma something, 4, and this one's going to be 1 comma 4, and I'm going to integrate from x to x. So I'm going negative 1 to 1, and that is what I would type into my calculator. Now, if it's easier for you, or just remember, because I'm going to have symmetry here, I could do half of this and rotate that half, and then it's going to double it just because of symmetry. Or I could say my volume is going to equal 2 times pi integral 0 to 1 of 4 squared minus x squared plus 3 quantity squared for my radius dx. Either one of these you can type into your calculator, and when you type these into the calculator, you're going to see that volume equals 48 pi over 5, or 30.159 for my decimal freaks, either one, okay? And that is how we are going to do it. Notice it's not a disc, it's a washer because there's a big fat hole in it, okay? That's revolving the x-axis, and remember, that's going to give me a dx. Well, what am I revolving on my next problem? My next problem, I'm going to revolve the y-axis, so this is going to be a dy. But let's graph this. Y equals x minus 1. Well, that's basically saying negative 1, here's 1. That is my y equals x minus 1. And I'm going to go, here's 1, 2, 3, 4, 5. And I'm going to bound by y equals 5, and, or x equals 5, and y equals 0. So my x equals 5. Here is my area in which I am going to rotate. I am going to rotate that area about the y-axis, which means my rectangles go to the y-axis. If I needed to draw my reflection, I will draw my reflection. That point's going to reflect to there. And 1, 2, 3, 4, 5, it's going to reflect out to here. And this line is going to be kind of coming straight up. This is going to reflect across, and it's going to be right there. There is my reflection of my solid, okay? And I can extend, because I'm rotating, this rectangle is going to rotate around to this side. And notice I can see I am going to have a hole in it, right? Well, when I rotate it, I'm going to have this little bugger in there, All right, that is my washer. That is half of my washer. Well, remember, volume equals pi integral a to b. When it's a washer, it's a major radius minus a minor radius. And in this case, we are going to be dy because my thickness is to the y-axis. That's how I know it's going to be a dy. Then all I'm going to do is I'm going to come down and I'm going to define what is big R, and big R is from my axis of rotation out to the curve. Well, how long is that? Well, if I'm thinking an x and a y, the length of that blue line is an x value, and it goes out to 5. So my big R is 5. My little r is what? Well, my little r is going to go from my axis of rotation to my inner radius. Again, it's an x value, and that x value is going to equal y plus 1. There's my x value. So y plus 1. And because it's a dy, I need my limits of y. Well, notice all these washers, they're going to start at 0, and they're going to go all the way up to here. Well, what is that point? Well, if I plug a 5 in for x, what is that y? When I plug that in, if I plug my 5 right in there, I get 5 minus 1. That's going to be 5 comma 4. So I am going to integrate from 0 to 4 is going to be what we're at. So I'm at my volume equals pi integral 0 to 4. And I'm going to do this. And I have my dy, and my big R is 5, and I need to square that, minus my little r is y plus 1, and I need to square that, and that is exactly what I'm going to type into my calculator. And when I type that into my calculator, hopefully you do so, you're going to find out this volume is going to equal 176 pi over 3, which is actually approximately equal to 184.307. Either answer is fine. And if you're trying to picture what does this thing look like, well, it kind of looks like one of these, if I can draw it. I'm going to try to draw it. And I'm going to have a top and a top. And in that top, I'm going to have on the bottom, I'm going to have this little hole drilled out, and that hole is going to go out like that, and it's going to be basically taking a little soup can and drilling something out with a hole all the way to the edge of the can, and this is going to be my solid there. The inside in here, this stuff is all cut out. That's all hollow in there. But you don't have to know what it looks like to see what it is. Last problem I think I am going to do here, and it is going to be the last problem I'm going to do here. So we are going to revolve the bounded area by y equals cosine x, y equals sine x, and x equals 0 about the x-axis. So this is going to be a dx, I know that. And in the end, what am I looking for? I'm looking for my integral pi from a to b of, I don't know what I'm after. Am I after a disk or am I after a washer? I guess I need to figure that out. And my picture is going to tell me what it is. So y equals cosine x, well that's starting up here at 1. And I know the cosine is down here at pi over 2. That's when it's on the x-axis, right? So this kind of comes down like so. And I know the sine x, my sine starts at 0. And I know at pi over 2, it's at its 1. And it's going to kind of come like this. Well, what is the only place these two meet? Well, that's going to be at pi over 4, isn't it? Because that's the only time the sine and cosine curves are the same. And it's really kind of a bad, like that. It's going to be like this. So I'm thinking that top one is a little bad, but it doesn't matter. It's not drawn to scale. This is going to be my pi over 4. So they are going to intersect at pi over 4, comma, root 2 over 2, there we are, and bounded by x equals 0. So this is my area in which is getting rotated, and that is getting rotated about the x-axis, so it's going like this, which means my rectangles are right here. There's my rectangles, which means if I clean this out a little bit so I can draw my reflection, try to draw it, they get harder and more complex as we go. So here's my 1, and this is going to kind of come down to about here-ish. This is going to kind of go like so. This one's going to kind of come, how is that one going to go? This top one's going to go like this too. Actually, it's going to go kind of the other way. This goes up, put that down. It's going to kind of come like this. And that's kind of how it's going to go. And if I extend my rectangle, you can tell I'm not very symmetrical because my rectangles aren't the same. But when I revolve that, and I revolve that rectangle, what happens is I go here, to here, to here, and I get these slices, these half washers that are in there. So then I'm going to see that my big radius equals what? Well, what is my big radius? It's from my axis of rotation out to this curve, where this curve, because that started at 1, that's my y equals cosine x. And because this vertical purple line, that's going to be an xy, it's a y value, that is going to be cosine x, which means if I get my little r is this little guy here, and that's from my axis of rotation to that curve. That curve right there is y equals sine x, and again, that's a vertical y, so my function is sine x, and when I write this integral, it's going to come out, my volume equals pi, and I'm integrating from here to here with a dx, and because it's a dx, I'm going from 0, and I'm going to end at, what is this? This is my x value, that's pi over 4, so I'm going to go to pi over 4, and then what I'm going to do is I'm going to take my big R squared minus my little r squared, because I can see I had a washer in here, and I'm just going to say cosine x squared minus sine x squared. So I'm going to type that into my calculator. And if you had to do this longhand, it's actually equivalent to this. This right here, when they're both squared, that is a cosine 2x identity dx, and I could type either one in. Most of the time, you are just going to be writing your integral situation. You're going to type them right into your calculator, and you are going to find out that this volume actually equals pi over 2, which is approximately 1.571 for the decimal freaks. And that's what we are looking at here, okay? We're revolving our area. We're not doing anything different. The only thing that's different is now there's going to be a hole in the middle. So I don't have a disc, I have a washer. And the washer method is right here. Big radius squared minus little radius squared. Okay, you got to square the radius. It's not the height of the rectangle. It is the difference of two disk methods. Big disk volume minus little disk volume. And from there, I'm going to let you work on some homework, and you should be able to tear into that 7.3b. And tomorrow, we are going to rotate any axis. I'll do about 3 problems and call her quits. Have a good rest of your day. Bye-bye.